Hello, this is my seventh lecture on graph theory. In this lecture, we will learn augmenting path algorithm to find maximum matching in bipartite graph. In the previous lecture, we have learned what is augmenting path. Augmenting path is an alternating path such that the path starts and end with a unmatched vertex. So, augmenting path is with respect to a matching M always. So, we will talk about augmenting path algorithm, and then we will also illustrate the algorithm using an example. Okay, so, here is the algorithm. Augmenting path algo. So, input to this algorithm is a bipartite graph G with X union Y and set of edges, and output is maximum matching M. Okay. So, this algorithm starts with a null matching. It starts with M null initially. So, M is the set of matching edges basically. So, initially your matching is null, there is no matching edge in the matching M, and then you try to find an augmenting path with respect to the current null matching. So, while there is an augmenting path P with respect to M, you do the following. You just update the matching. So, you will learn that how every time you find an augmenting path, the matching size will increase by 1. So, this is M is M symmetric difference P. I will explain all these things. So, this symmetric difference means it is a this is a set of edges, this is also a set of so P in terms of set of edges, P minus M minus P union P minus M. This is called symmetric difference, and you are out of this loop when there is no augmenting path with respect to the current matching, and then you return M. Well, so this is the same graph that we considered in the previous class. Let me illustrate this algorithm with respect to this graph given here. We will try to find maximum matching in this bipartite graph. So, illustration. So, at the first iteration what we do is that, as I said, that this algorithm start with a null matching. So, M is equal to phi, it is a null matching, there is no edge in the matching, and then you try to find an augmenting path P. Okay. So, here the augmenting path could be just any in all the edges are unmatched. Okay. So, you can just pick any one edge arbitrarily. Let me pick say G1 B1. This is an augmenting path because as I said that an augmenting path is an alternating path which starts and ends at unmatched vertices. So, this P the augmenting path P given here, that is G1 B1, it is an alternating path. It consists of only one edge, and it start with an unmatched vertex G1 and ends at unmatched vertex B1. So, at this moment nothing is matched. So, everything is unmatched. So, this is an augmenting path. Now you update your M. So, M is, as I said, M is M symmetric difference P, that means M minus P union P minus M. So, here M minus P is, M is null. So, M minus P is also null, and P consists of this G1 B1 and M is null. So, this is P minus M is consist of this edge G1 B1. So, this is your current matching. Okay. So, let me just denote that okay, this is your current matching. Now, at the second iteration, you have a matching M and you have to find an augmenting path with respect to this matching. So, I could not give an example of an augmenting path in my previous lecture. Now, I will give. So, I have to find an augmenting path with respect to this matching now. So, this is an augmenting path, say B4 G1, B4 G1, then G1 B1, G1 B1, and then B1 G2, G2. So, B4 G1 B1 G2, this is an augmenting path because this is an unmatched edge, matched edge, unmatched edge. So, it is an alternating path, and this path starts at a unmatched vertex B4 and ends at another unmatched vertex G4. So, this is an augmenting path. Well, so you are inside this loop because still with respect to the current matching you have a augmenting path. So, you update your M now. As I said, every time you update M, the cardinality of M will increase by 1. So, initially the cardinality of this M was 0, and then the cardinality of this matching is equal to 1. Now, we will say that the cardinality of this matching will become 2. So, M is again M symmetric difference P, whereas M is this one and P is this one. So, M minus P is null. M minus P is null because M has this edge and you are subtracting or removing this edge from this set, union P minus M. So, P is this set of 3 edges basically, and then you remove this edge from here. So, this will be consist of two edges now B 4 G 1 and B 1 G 2. So, these are the two edges now in your matching. So, your matching size has become now equal to 2. So, that is I told before that every time you augment augmenting path, the size of the matching will increase by 1 at every step. So, let me just then see this is no more. So, G 1 B 1 is no more an edge a matching edge. So, what I will do is that I will remove that edge now. This is not a matched edge. Let me draw this link. Okay. So, now the matched or matching edges are B 1 G 2, B 1 G 2, B 1 G 2, this is a matching edge, and the other one is G 1 B 4, G 1 B 4. Okay. So, I have a matching of size 2 at this moment. Let me see whether there is an augmenting path with respect to this current matching. Okay. One can try to find an augmenting path with respect to this current matching. So, you have to start with the unmatched, there could be several, you have to start with an unmatched vertex. So, let me start with let me consider this augmenting path, that B 5 G 1 and then G 1 B 4, G 1 B 4 and then B 4 G 3, B 4 G 3 and let me use a bracket here also. That is all. This is an alternating path because this is unmatched, this edge is matched, this is matched edge, this is unmatched edge, this is unmatched edge, and this vertex B 5 is unmatched vertex and G 3 is also unmatched vertex, right. B 4 G 3, right. So, G 3 is also unmatched vertex. So, one thing to observe is that when you are finding an augmenting path with respect to a given matching, it not necessarily that this augmenting path will include all the matched edges in the matching. So, here you can see that this augmenting path P, it includes only one matching edge G 1 B 4, but this path does not include this edge B 1 G 2 is not included in this augmenting path. So, anyway, this is a augmenting path. Now, we augment this one in the current matching. So, you update your M now. Okay. So, M is M minus P and union P minus M. So, M minus P is M minus P. You can see that this is B 1 G 2, B 1 G 2 is there and G 1 B 4 is cancelled. So, this one union P minus this, again this will be cancelled, this 2 will be cancelled, and you will be left with G 1 B 5 and B 4 G 3. Okay. So, now you can see that your matching is having cardinality. This has 3 matched edges, B 1 G 2, G 1 B 5 and B 4 G 3. So, what I will do is that I will update my colors here also. So, G 1 B 4 is no more matched edge. So, I will remove this thing. I will remove that thing. Now, the new matched edges are G 1 B 5, G 1 B 5 is the new matched edge, and G 3 B 4 is another matched edge, right. Now, with respect to this matching, now can you find an augmenting path? That is the next iteration. Can you find an augmenting path with respect to the current matching? Now, the cardinality of this matching is equal to 3. Yes, so you can find this augmenting path. You can check that this is an augmenting path B 2 G 3, B 2 G 3, G 3 B 4, G 3 B 4 and B 4 G 4, B 4 G 4 is an augmenting path, because this is a matched edge, these are unmatched edges, and this is an unmatched vertex, B 2 is also an unmatched vertex. And if you augment this one, you can check that your new matching will be this one, B 1 G 2, this will not be affected, G 1 B 5 will not be affected, and then you will have B 2 G 3 and B 4 G 4. So, this is the new matching with respect to the current augmenting path B 2 G 3. Let me just draw it finally. So, this has been removed, B 3 G 4 has been removed. Okay. Now, B 2 G 3 is the new matching, and B 4 G 4 is another new matching edge. So, the cardinality of M at this moment is equal to 4, but that is not the stopping criteria. Now, you try to find an augmenting path with respect to this matching. You can check that you will not find an augmenting path with respect to this matching. So, no augmenting path, because the obvious observation that all the girls are matched. So, you will not get an augmenting path. Augmenting path is always from one unmatched boy to one unmatched girl. So, since all the girls are matched, no augmenting path with respect to the current matching M. So, you stop here. Okay. So, this is the end of this algorithm, and we have explained augmenting path algorithm with respect to one example here. Next, we talk about why this algorithm is correct, why the stopping criteria is that you stop when there is no augmenting path with respect to current matching, you stop there, and that is the maximum matching, and you return that M. So, why this is true? That is sort of will give a proof for this one, that M is a maximum matching if and only if there is no augmenting path with respect to M. So, if we can prove this theorem, that proves the correctness of this algorithm. Before proving that theorem, I want to talk about another result, which is stated here. So, I will talk about this theorem. I am considering two matching. The statement of the theorem, let me write, slightly difficult, but very useful theorem, that every component of the symmetric difference of two matchings is a path or an event cycle. Okay. So, we need to understand this statement of this theorem. Let me illustrate the statement of this theorem using an example. Let me consider this graph. So, I am talking about symmetric difference of two matchings, and what are the properties of that graph, which is just a symmetric difference of two matchings. Okay. So, this is the graph we are going to consider. Now, there are two matchings I will talk about of this graph. Let me just denote them by different colors. So, this is one matching, maybe this is the red color matching is matching M, and so this is a matching, and so the M, this is the matching M, and I will consider another matching, which I will denote by blue color. So, this is part of the other matching M prime. Note that they satisfy the property of the matching. This is M prime. Okay. So, the M prime is the blue color matching. Okay. So, I hope that there is no doubt with the statement that M is a matching, because you can see that every vertex is adjacent to at most one matched edge in matching M. Okay. So, that is why M is a matching. So, this vertex is with respect to the red matching, this vertex is matched with this matching edge. This vertex is not matched with any. So, this is unmatched vertex with respect to the red matching, right. Well, so now if I take the symmetric difference of these two matching, let me label them also. So, this is A, B, C, D, E, F, G, H, I, J, K, L. So, my M consists of these edges A B, E C, D F, G H, J K, right, and my M prime consists of A C, B D, E F, G H, I J, G H I J, and K L. Okay. Now, you consider the symmetric difference. So, I am concerned about the component of the symmetric difference. I will take the symmetric difference of these two matching, M symmetric difference M prime. You see that the only common thing is G H. So, the symmetric difference will consist of all the edges except G H. Okay. So, M symmetric difference M prime will be consist of A B, E C, D F, not G H, because this minus this will cancel G H, J K, and similarly here also when you compute M prime, because this symmetric difference means it is M minus M prime union M prime minus M. So, when you compute M prime minus M, only G H will cancel out, all the other edges will be there. So, this is A C, B D, E F, not G H, I J, and K L. So, this is the symmetric difference of these two matchings. Now, let me call this one as F. So, this is a graph, right. It has some vertices and edges, and I draw this graph again. So, this is my F graph, which is the symmetric difference of these two matchings. Okay. So, this is A, B, C, D, E, F, and then you can see that G H is not there. So, I will just remove those two vertices also. So, I will be left with I J K L, and again I will use two different colors for, because this is due to the matching M, 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 and this edge is due to the matching M prime, matching M prime, matching M prime, matching M prime, matching M prime. So, this is a beautiful result. Now, what now you can see the claim, now you understand the statement of this theorem, that every component of the symmetric difference of two matchings, here the two matchings are M and M prime, is a path or an event cycle. You can see that. So, this is the graph which is the symmetric difference of two matchings M and M prime. You can see that this is one component of this symmetric difference, or this is the graph F basically, which is the symmetric difference of M and M prime. You can see that one component is a event cycle and the other component is a path. This is a path basically, right. Now, this example will help you to understand the proof of this theorem. So, proof of this one, let F be the graph which is the symmetric difference of M and M prime. Now, it is an easy observation. I will just write down the statement and then I will explain that every vertex has at most one incident edge from M minus M prime, that is mostly from M. Okay, so, every vertex has at most one incident edge from M minus M prime and one incident edge from M prime minus M. Let me at least explain this line from this example. Look at a vertex, it has at most one edge from, this is an edge from M minus M prime and this is an edge from M prime minus M. So, that is what it says, that every vertex has at most one incident edge from M minus M prime and one incident edge from M prime minus M. Look at this vertex, I said at most. So, this vertex does not have any incident edge from M minus M prime, but it has a incident edge, blue color edge from, this is an edge from M prime minus M, but no edge from M minus M prime. Okay. So, this implies that every vertex can have degree maximum 2, thus we write delta F. See, this delta is different, this delta and this delta are different, this is the symmetric difference and this is the notation for capital delta is the notation for the maximum degree of the graph F. So, the maximum degree of the graph F is now 2, it is at most 2. So, since the maximum degree is at most, maximum degree is 2, every component of the graph, every component of F is either a path or a cycle. This is a easy observation. Further, you can see that the statement of this theorem that it is not only cycle, it has to be an even cycle. Okay. So, that part we will prove now. Further, the edges of every path and cycle in F alternate between edges of m minus m prime and m prime minus m. This is true. So, you can see that in a path. So, if there is a path, that path is an alternating path. The edges will be, one edge will be blue edge, the next one will be red, again blue, red, like that, and that is true also. The cycle is also an alternating cycle. It can't happen that you have two, here also it is a blue edge, that is not possible, but then this is not a matching. Okay. So, that is from the definition of the matching. So, the cycle is an alternating cycle, the path are also alternating path, and since the cycle is an alternating cycle, thus the cycle has even length. Thus, the cycle has even length. Okay. So, this is a very important result according to me at least, that every component of two matchings, you take two matchings m and m prime, and the symmetric difference of two matching will give you a graph, and the components of the symmetric difference of two matchings are either a path or it is a even cycle. We will use this result to prove that important theorem, that a matching is maximum if and only if there is no augmenting path with respect to that matching M. Thank you very much.